Yes, children. In the previous lesson, I spoke about Bohr's postulates, and there we saw what is the energy of an electron belonging to nth orbit, and I gave you this formula minus 2 pi square m z square e power 4 upon n square h square. Now, taking into consideration 2 pi square m z square e power 4 and h, all these things to be a constant, this comes out to be minus 1312 upon n square. So this is kilojoule per mole. Here you try to remember m is mass of electron, z is atomic number. Here, since we are talking about hydrogen, z is equal to 1 we take, and E is nothing but charge of electron, that is 1.6 into 10 power minus 19 coulomb, and H is Planck's constant, which is 6.626 into 10 power minus 34. So putting all the values, you get this particular formula. Now this is kilojoule per mole. Now if you want to have kilojoule per atom or joules per atom, then what you do? You have to divide this by Avogadro number. First of all, kilojoule, you want to convert it into joule, then it would be minus 1312 into 1000 upon n square. And if you want to convert per mole into per atom, then you have to divide this by Avogadro number, which is 6.02 into 10 raised to power 23. So this whole thing, when you solve, you will get minus 2.18 into 10 power minus 18 joules per atom upon n square. So this is nothing but energy of an electron belonging to nth orbit, any orbit, it may be 1, 2, 3, anything. Okay, so now based on this, I already told you, according to this Bohr, when energy is absorbed, the electron moves from a lower level to a higher level, and when energy is released, electron moves from a higher level to lower level. Now let us see this particular concept in terms of numerical values. Now see, this is change in energy. That is, whenever there is an electron transition from one level to another level, the change in energy is denoted as delta E. Now delta E is equal to what? Energy associated with final position minus energy of electron associated with initial position, that is E final minus E initial. So this is change in energy. So the electron transition, when it is taking place from higher to lower level, what is the change in energy associated with it? So when when electron is going from lower to higher, energy is absorbed, and when an electron is coming from a higher level to a lower level, energy is released. That is, energy is emitted, right? Okay. Now what I gave you, energy of an electron belonging to nth orbit is given by the relation minus 2.18 into 10 power minus 18 joule, and this value is nothing but the Rydberg constant, that is denoted as minus RH, right? So Rydberg constant value is this, and there is already this minus sign, I already told you this, right? So that is minus RH into 1 upon n square, because electron is belonging to some level, that is n. Now supposing if it is belonging to the first level, that is your cation, then it is minus RH into 1 upon 1 square. Now remember that these things we are talking in terms of hydrogen. So it will be minus 2.18 into 10 power minus 18 joule only. Now if it is energy of an electron belonging to nth orbit, then it is minus 2.18 into 10 power minus 18 into z square by upon n square joules. Why z square? It is for atoms other than hydrogen. So if it is any other atom other than hydrogen you are referring to, then the atomic number of that atom has to be mentioned here, or has to be included here. Okay, now let us see, an electron is undergoing transition from one level to another. So one level to another. So that the first level is taken as initial, and the where it is undergoing transition, that is called as final level. And I already gave you this relation, delta E is equal to E final minus E initial. Now let us put the energy value as minus RH. So what you will get? Minus RH into 1 upon electron belonging to final level square minus of minus RH into 1 upon the electron belonging to the initial level, that is Ni square. So N final square, and here it is N initial square. Now this is E final minus E initial. So that is what I have represented here. Now minus of minus will become plus. So this will be minus RH into N upon 1 upon N final square plus RH into 1 upon N initial square. Now rearrange this expression. So you will get RH into 1 upon N initial square minus 1 upon N final square. So this is what you will get. Now what is the value of RH? It is 2.18 into 10 power minus 18 into 1 upon N initial square minus 1 upon N final square. Now come to this understanding. What is delta E? Delta E is nothing but h nu. So if delta E is h nu, what is nu equal to? Nu is equal to delta E upon h, right? So here what I have done, if I am dividing delta E by h, that is nothing but nu. So if I am going to divide delta E by h, I have to do it on both the sides. So that is what I have done. Delta E upon h is equal to 2.18 into 10 power minus 18 upon the value of h is put here into 1 upon N initial square minus 1 upon N final square. Now when you solve this expression, you will get 3.29 into 10 power 15. So this second will come up, joule and joule will get cancelled, you will get second inverse into 1 upon N initial square minus 1 upon N final square, right? Now what is this equal to? This is equal to delta E by h. What is it? It is equal to nu. Now again come here. Nu is equal to what? C by lambda. The C by lambda I have put it as 1 upon lambda, and 1 upon lambda is what? Nu bar. Is it not? Inverse of wavelength is nothing but nu bar. That is wave number. So wave number is equal to what? What is wave number from here? Wave number is nothing but delta E upon hc. That's what I have put here. And you know very well that this delta E upon h, delta E upon h is nothing but nu. This we already know it. So what is nu bar? Nu bar is equal to nu by c. Okay. So what we have done, delta E upon h is nothing but nu. So what I am going to do in the next step, I am going to divide nu upon by c. So when I divide by c on this side, I will have to divide by c on this side also. So 3.29 into 10 power 15 upon 3 into 10 power 8 meters per second, that is the velocity of light, into 1 upon n initial square minus 1 upon n final square. So this value, this is coming out to be 1.09677 into 10 power 7 meter inverse. Second inverse gets cancelled, so meter inverse you will denote. That is into 1 upon n initial square minus 1 upon n final square, right? Now the next thing that you have to understand here is what you need to know. You need to know that supposing if it is an absorption spectrum, during absorption what happens? Electron goes from a lower level to a higher level. So n final will be greater than n initial. So in that case what will happen? So this is your relation. So n final is greater than n initial. So if this is greater, so this whole thing will be lesser. So your delta E or whatever value you are finding out for change in energy, that will be positive. So if delta E comes out to be positive, that shows it is an absorption spectrum. And if it is emission spectrum, then in that case n initial will be greater than n final, because during emission what happens? Electron from a higher level comes to lower level. So when it is Ni greater than Nf, if this is greater, then this whole thing will be lower. So in that case what will happen? Your delta E will be negative. That shows that, from the value of delta E that you are finding out, delta E means initially you will go by this. This is not with reference to wave number, we are finding out with reference to energy. So in that case, if it comes out to be negative, it shows that it is emission spectrum, and if delta E comes out to be positive, it shows that it is an absorption spectrum, right? So this is about the relationship that you need to know, that is given in your text also. I just derived how you got this. So here also the same thing is given. In the case of absorption spectrum, N final is greater than N initial. On the other hand, if it is emission spectrum, then N initial is greater than N final. So delta is E will be negative in that case, right? So you need to know how to do the problems based on this. Now what we have to do is, we need to know now what are the limitations of Bohr's model. What are the limitations of Bohr's model? Limitations, when you consider it doesn't tell you anything about multi-electron systems. That is one important thing. It does not tell you anything about multi-electron system, because he is talking about only hydrogen and hydrogen-like atoms. So that is one important issue with reference to Bohr's model. Then apart from that, it could not explain the ability of atoms to form molecules by chemical bonds. Why at all atoms are joining together through chemical bonds? So this was also not explained by Bohr. And apart from this, Bohr's theory was unable to explain the splitting of spectral lines in the presence of magnetic field and electric field. So this I gave you briefly in the previous video lesson also. What are the limitations of Bohr's model? Now, what is the failure of Bohr's model? What is it leading to? Let us see. Now, according to Bohr, you know that an electron is considered as a charged particle moving in well-defined path, that is orbits, around the nucleus. And Bohr's model is not considering wave character. If orbit is a clearly defined path, then position and velocity of an electron should be known at the same time. If orbit is a well-defined path, then where is the position of electron and what is the velocity of electron? It should be known at the same time. Now, such a thing is not possible according to Heisenberg. That means Heisenberg is another scientist who went against the Bohr's model. That means he says that, Heisenberg says that Bohr is not considering the dual nature of electron. So Bohr's model ignores the dual behavior as well as it is contradicting Heisenberg. So Heisenberg asked that if it is having a well-defined path, then position and velocity should be known, and why we are not able to measure. How can you measure the velocity of electron if you know the position, or if you know the velocity, if you know the position, then how is it that you are not able to measure the velocity of electron? So the aspect of Heisenberg, it was considered as a major factor, and this was one big reason why Bohr's model failed. Then later on came another scientist by name de Broglie, based on dual behavior of matter and Heisenberg uncertainty principle. So these two things have to be considered if you want to explain the model of an atom. So what did de Broglie say? He said in the year 1924, matter, like radiation, it is also exhibiting dual behavior. Matter is also showing dual character. Like photon, electrons should also have momentum as well as wavelength, he said. Electrons should also have momentum as well as wavelength. That means momentum means particle nature, wavelength means wave nature. So if both the things have to be expressed, then how did he connect both? You know very well that E is equal to mc square according to Einstein. And you also know E is equal to h nu, which is according to Planck's constant, Planck's equation. Now, This is also energy. This is also energy. Now both the energies, if they are equated, you will have mc square equal to h nu. Now you know very well that nu is equal to c by lambda. Now if you put nu, replace it as c by lambda, then 1c is going to get eliminated. With the result you will get lambda is equal to h upon mc. Now this c is nothing but velocity of light, which we are considering as velocity of electron here. So h upon mv. So mv is nothing but momentum. Product of mass and velocity is momentum. So this can be written as h upon p. So you are having now wave character also and particle nature also. That means electron is showing dual character. So this is what is called as de Broglie relation. This is lambda is equal to h upon p or h upon mv, where lambda is nothing but wavelength showing the wave nature, and p is nothing but momentum, which is equal to mv, which is showing the particle nature of electron. Now what did Heisenberg say? Heisenberg said that it is not possible to determine simultaneously the exact position and momentum of an electron to absolute accuracy. This was his contention. If you are able to measure the position, then you cannot measure the velocity of electron, or if you are able to measure the velocity of electron, you cannot define its position. So that is his contention. That is called Heisenberg uncertainty principle. This is uncertainty. You are not certain about the position of electron if you know the velocity, or if you know the velocity, or if you know the position, you are not certain about the velocity of electron. So that is given by the relation product of the two uncertainties, that is delta x into delta p. Delta x is nothing but uncertainty in position, and delta p is uncertainty in momentum. So the product of these two uncertainties is greater than or equal to h upon 4 pi. So what is delta p? That is momentum, change in momentum. Change in momentum is due to change in velocity, because mass of that particle will be constant. So that is delta x into m into delta v greater than or equal to h upon 4 pi. So if you take mass this side, then the product of uncertainties in position and velocity is greater than or equal to h upon 4 pi m. So this is what is the contention of Heisenberg. So that is what he told. Right? Now, the wave particle duality of matter and be consistent with Heisenberg came with the advent of quantum mechanics. Now totally a new theory was developed, that is called as quantum mechanics, which is based on electron behaving as a particle as well as a wave. So this was developed independently by Heisenberg and another scientist by name Schrödinger. Both of them developed this theory. Schrödinger, he gave an equation whose solution gave an insight into the structure of atom with the position of electrons. So this was a major breakthrough in the discovery in understanding the structure of an atom. So what it is, when an electron is in a particular energy state, the wave function corresponding to that energy state contains all information about the electron. So this is the concept of this particular theory, that is quantum mechanics. Now each and every energy state, your K shell, L shell, M shell, they are all called as energy states. Luckily, you need not have to know about the Schrödinger equation. You just have to understand that Schrödinger has given, his contribution to quantum mechanics, his contribution to electronic structure of an atom is very well to be understood, but at a higher level. When you go to higher classes, that time you will have to learn. Right now, it's enough that if you understand that when an electron is in a particular energy state, the wave function corresponding to that energy state, it contains all the information about the electron. Like if I say the electron is belonging to K shell. Now K shell is at a particular distance from the nucleus. Right, so distance of the electron from the nucleus is clear. Then where is that electron? In what way it is represented? Is it spherical or is it in some other shape? All that is understood. That is, you try to get the address of an electron if you understand this Schrodinger equation. So the quantized energy states and their wave functions are characterized by three quantum numbers. Wave functions, they are represented by the letter, this is called as psi. P is silent here, it is called as psi. Quantized means measured. I already told you about this. Quantized energy states and their wave functions put together, they are characterized by three quantum numbers. And what are they? They are principal quantum number, azimuthal quantum number and magnetic quantum number, that is N, L and ML. Now the probability of finding an electron at a point within an atom is proportional to the square of the orbital function. So the probability of finding an electron at a point within an atom is what is called orbital. The space at which the electron is present. What is that space called? That space is called as an orbital. An orbital is there in an orbit. Now we need to know about the different quantum numbers and their significance. Okay, now what are the different quantum numbers? The different quantum numbers are principal quantum number, which is represented by the letter N. Then you have azimuthal quantum number, which is represented by the letter L. This can also be called as angular momentum quantum number. Then the third one is called as magnetic quantum number, which is represented as ML. And the fourth one, these three actually represent the complete picture about an electron. The fourth one is called as spin quantum number. This was found out at a little later stage. This is given by MS. That is spin quantum number. So these are the different quantum numbers which help you to understand or which help you to decide the address of an electron, or you come to know of different things about an electron. Okay. Now this principal quantum number, what is this principal quantum number? It is the distance of the electron from the nucleus. That is called as principal quantum number. Distance of the electron from its nucleus, that is called as principal quantum number. That means when you talk about K shell, L shell, M shell, this is your, say, the nucleus, then this is your K shell, this is your L shell, this is your M shell. Now what is the distance of the electron from the nucleus? So this is what is called as principal quantum number. So that is basically your shell number, that is K shell, L shell, M shell, or you can also call it as n is equal to 1, n is equal to 2, n is equal to 3. Like that also you can say. So it gives you the average distance of the electron from the nucleus. So what is your n? It gives you the distance of an electron from its nucleus. And it also determines the energy of electron. Again, hydrogen was taken as standard, and hydrogen-like atoms were taken as standard, because electron transition, if it is just one electron, it's very easy to understand the concept when you are talking about electron transition. So it is also telling you about the energy of electron. So first point is that it gives you the distance of electron from the nucleus. Then it is also giving you the energy of an electron belonging to nth orbit, which we already saw that it is minus 2 pi square m e power 4 upon n square h square. I am not talking about Z because we are talking about hydrogen level. Then it also tells you how many electrons may be present in any particular shell. So it is also telling you the number of electrons accommodated in a shell. Now this you have studied in your 9th class also. This is given by the relation 2n square, where n is the shell number. That means K shell can accommodate 2 into 1 square, that is equal to 2 electrons only. L can accommodate 2 into 2 square, that is it can accommodate 8 electrons. M means 2 into 3 square, so that will accommodate 18 electrons. 2 into 9 is 18, like that it goes. So this is about the significance of principal quantum number. It tells you the distance of the electron from the nucleus, it tells you the energy of the electron, and it also tells you how many electrons can be there belonging to a particular shell, belonging to a particular quantum number. Now, what is the significance of L? L tells you the number of subshells present in the main shell. That is, K shell contains how many subshells. That is given by L. Now, how many subshells? Say, if n is equal to 1, that is your K shell. If n is equal to 1, what is the value of L? L is equal to 0. That means this 0, what does it say? L carries a value which is 0 to n minus 1. The value of L ranges between 0 to n minus 1. Now what is the value of n here? It is 1. So what is 1 minus 1? That is 0. That is why I put the value of L to be 0. Right? Now supposing if n is equal to 2, then what will be the values for L? Again, L is equal to, I told you, 0 to n minus 1. Now 0 to n minus 1, that means 2 minus 1 is 1. So how many values for L you have? You have 0 and 1. 0 is a value. I told you 0 to n minus 1. So you have two values for L. For n is equal to 2, that is your L shell. They are 0 and 1. Now supposing if n is equal to 3, then L is equal to 0, 1 and 2. Again it is 0 to n minus 1. n minus 1 means 3 minus 1, that is 2. So this is one particular thing that L signifies, the number of subshells present in the main shell. How many subshells are there in the first shell? There is only one. Now try to understand that if I write 0, don't ever consider that there is no subshell. 0 is a value for L. That means there is only one subshell. How many values are there? 0 is a value. So this value is counted as 1. That means how many subshells are there? Only one subshell. So corresponding to n is equal to 1, there is only one subshell. Same way corresponding to n is equal to 2. How many subshells are there? 0 and 1. That means 2 subshells are there. Now if it is n is equal to 3, then how many subshells are there? 0, 1, 2. That means this will correspond to 3 subshells. Right? Now apart from this, what is the other significance of this L? It also tells you the angular momentum of the electron present in any subshell. So this is one other significance that azimuthal quantum number gives you. And it also gives you the relative energies of the various subshells. This also it tells you. Not only this, it also tells you the shapes of various subshells. That means subshells are of many types. It's not of the same kind. There are different kinds of subshells. Now, how do you designate a subshell based on the value of the azimuthal quantum number? Say you have value of L, and then what is the what you designate that value? Designation of subshell. Now supposing L is equal to 0, then it is designated as S subshell. If the value of L is 1, then how do you designate that subshell? You designate it as P. If you have a value of L as 2, then the designation for that subshell is D. If the value of L is 3, then you designate that subshell as F. So that's how it goes. So when I say n is equal to 1, L is equal to 0, there is only one subshell. Which subshell? 0 corresponds to S subshell. Now when n is equal to 2, L is equal to 0 and 1, I told you that it is corresponding to 2 subshells. 0 corresponds to S subshell and 1 corresponds to P subshell. So there are 2 kinds of subshells in the second shell, that is S and P. Now if you come to third orbit, then you have 0, 1, 2. So 3 different kinds of subshells are there. What are they? They are S, P and D. So like that it goes. So if you consider n is equal to 4, then what is the value of L? L is equal to 0, 1, 2, 3. 0 to n minus 1. So 4 different subshells are there in the fourth orbit. What are they? They are S, P, D and F. These are the 4 subshells. Now let's come to the next one, that is magnetic quantum number. Now what is magnetic quantum number? This is denoted as ml. Now what does it signify? Magnetic quantum number signifies the orientation of an electron. Orientation of electron. Or you can say this orientation corresponds to orbital. I told you orbital is the probability of an electron around the nucleus in space. That is called as orbital. Orientation corresponds to orbital. Each orientation corresponds to an orbital. So this ml, what does it tell you basically? It tells you the number of orbitals present in any subshell. Now how will you find out the number of orbitals? Just like I said, if n is equal to 1, then L is equal to 0, because the value of L, it is ranging between 0 to n minus 1. Same way, what is the value of ml? ml is also equal to 0 here. Why? Because the value of ml ranges between minus L through 0 to plus L. So if L is equal to 0, ml also is bound to be 0. Now supposing if I take n is equal to 2, then L will have two values, 0 to n minus 1. So L will have value 0 also. L will also have a value 1. There will be two values. Now if L is equal to 0, ml is also equal to 0. And if L is equal to 1, then ml will be equal to what? Minus L to plus L. Now L is 1 means minus L is what? Minus 1 through 0, that is minus 1, 0, plus 1. So how many orbitals are there belonging to a particular subshell? Subshell is P. And how many orbitals correspond to that subshell? 3, minus 1, 0, plus 1. So how to calculate how many subshells? This is equal to 2L plus 1. So if you put the value of L is equal to 1, 2 into 1 is 2, 2 plus 1 is 3. So you're getting 3. Now if you put the value of L is equal to 0, then 2 into 0 is 0, 0 plus 1 is 1. That means there is only one orbital corresponding to L is equal to 0. So L is equal to 0 corresponds to S subshell. So how many S subshells are there in the second orbit? There is only one S subshell, because ml is having only one value, that is 0. Whereas how many orbitals are there in the P subshell? P subshell has 3 orbitals, minus 1, 0, plus 1. So how many subshells is given by the relation 2L plus 1? What are the subshells? That is given by the range, that is minus L through 0 to plus L. So we have to be very clear with this. So there is only one orbital in the first shell. There are 4 orbitals in the second shell. What are they? Here there is only one orbital, which is s orbital. Now this s orbital belongs to first shell. It's only 1 in number. And here you are having 0 corresponds to s orbital. Now this s orbital belongs to second shell, so you write it as 2s. And this 1 corresponds to p. Now this p subshell is belonging to second shell, so you write it as 2p. And how many p orbitals are there? They are 3 in number, which are denoted as 2px, 2py and 2pz. These are the 3 orbitals. Right? So, if you want to sum up this particular concept, if I write subshell and the number of orbitals corresponding to that, if the subshell is s, the number of orbitals belonging to s subshell is only 1. If the subshell is p, the number of orbitals belonging to that is 3. If the subshell is d, the number of orbitals corresponding to d subshell will be 5. If the subshell is f, then the number of orbitals corresponding to that is 7. Now you can relate this as 2l plus 1. Use this relation 2l plus 1. So if it is s, that means l is equal to 0. If it is p, then l is equal to 1. If it is d, then l is equal to 2. If it is f, then l is equal to 3. Now correspondingly you can put 2 into 0 plus 1 is 1. 2 into 1 plus 1 is 3. 2 into 2, 4, 4 plus 1 is 5. 2 into 3, 6, 6 plus 1 is 7. So this is how you get the number of orbitals. Now one other concept that you need to know is, now when you show 3 orbitals belonging to p subshell, all these 5, all these 7, they are all called as degenerate orbitals. Degenerate orbitals means orbitals having same energy. Right? Now coming to the last one, that is spin quantum number, which is denoted as ms. Now each orbital, whether it is belonging to s subshell or p subshell or d subshell or f subshell, whatever it may be, whichever subshell the orbital belongs to, each orbital has the capacity to accommodate only 2 electrons. Each orbital has the capacity to accommodate only 2 electrons. So here you see now each orbital can accommodate only 2 electrons. Now n is equal to 1, that is k shell. K shell is having only one orbital, and that one orbital is called as s. and that can accommodate only 2 electrons. You know very well that K shell can accommodate only 2 electrons according to n square concept also. Then come to n is equal to 2. It is having 4 orbitals, 1, 2, 3, 4. 1 s and 3 p's. So together it is counted to 4 orbitals. That means it can accommodate 8 electrons. This can accommodate only 2 electrons, and this can accommodate 8 electrons. And if you go towards the next, that is n is equal to 3, then n is equal to 3 means L is equal to 0, 1, 2, because it ranges between 0 to n minus 1. Then what is your ML? ML says that it is minus L to plus L. Each and every value you have to count like that. If it is 0, minus 0 or plus 0, it is only 1, that is 0. Then corresponding to 1, it will be minus 1, 0, plus 1, that is minus L to plus L. Now when you come to 2, it is minus 2, minus 1, 0, plus 1, plus 2. So here what you find? You find here one orbital, that is S. Now that S belongs to third shell, so you write it as 3s. Now this 1 represents P. L is equal to 1 means P, I told you, that is P. Now this P belongs to third shell, that is 3P. They are 3 in number. Then L is equal to 2 means it is D, and that corresponds to third shell, so you call it as D. I told you each orbital has the capacity to accommodate only 2 electrons. So S, it's only 2 in number, and P, since they are 3 in number, then each carrying 2, so 2 into 3 is 6 electrons. And here it is 5, each carrying 2, so 5 into 2 is 10. So put together you will get 18. Now according to 2n square also, 2 into 3 square is 18 only. So this is how it is calculated. Right? Then we will continue in the next lesson.